Namaskar my dear friends. Let us talk about S32K microcontroller. I am going to take a series of S32K 118 with 64 LQFP package. Okay. We have already seen S32K 118 with 48 LQFP package. A lot of circuits were there. So first of all we'll just see a very brief discussion about it and then we will see the circuit. Okay. So this is the complete block diagram that I will be discussing. So as you can see, this is a microcontroller from NXP S32K series, and the complete part number for this is this one, which is going to be FS32K 118 LAT0 MLHT. So LH is actually denoting 64 pin and LF is denoting 48 pin. Okay. It is Cortex M0 plus 48 megahertz to 56 kilobytes of flash. Okay. It is having CAN FD, Flex IO. Flex IO actually helps you to map your like UART signal or SPI signal to any pins that you want. Okay, because a corresponding pin may not be applicable, and it is having CSC security and all those things. Okay, so if you wish to reach out to us, you can always connect to us with on this number and as well as on this particular email ID. Okay, for any design that you require. If you see, once you go to the home page of this particular microcontroller on NXP website that I will be giving you in the description box, so you will see this particular understanding like S32K1 microcontrollers for automotive general purpose. If you see a brief idea about like what are the operating features for this particular microcontroller, you can see all the like features and availability that is there with this microcontroller. So as you can see, we have number of cores, that is 1. We have core type as Cortex M0 plus. We have operating frequency as 48 megahertz. We have flash as 256 kilobytes, SRAM for 25 kilobytes. We have EEPROM as well, which is inbuilt EEPROM, that is 2 kilobytes. Now if we see about the serial communication, so one I2C, that is I2C is there, then 2 SPI is there, 2 UART is there. Okay. If you talk about GPIOs, we have total 58 numbers of GPIO out of 64 pins. You can use 58 pins as GPIOs. We have one CAN, then we have one CAN FD, but any one of them can be used, not both of them together. We have HMI, that is human machine interface, that is flexible input output is available. Then we have security modules, we have timers, we have PWMs, we have ADCs. 2 ADCs are there in this. Okay, sorry, it is one ADC is there with 12 bits and 16 channels are there total. We have one DAC as well. The supply voltage is 2.7 volt to 5.5 volt. It means you can utilize this particular microcontroller for a design of 3.3 volt logic level as well as 5 volt logic level. So any of these two power supply you can utilize for this particular microcontroller. And it is a automotive qualified, so it can be utilized in automotive applications. Now let us talk about the applications that is recommended from the manufacturer's website. So you can see we have automotive applications, lot of them are there, and once you go on this particular website you will be able to click any of the applications to find the exact circuits related to that. Okay, anyway, we have a lot of applications like electric pumps or firmware over the air. We have hybrid electric vehicles applications. Very good thing is we have like automotive advanced exterior lighting and all those things. It has other applications like industrial applications and home appliances and all, basically motor drivers and major home appliances like uh, fridge, washing machines, mixtures and all those things, that is there. Motor drives is one of the like most important application that is there for this particular microcontroller. Alright, so what we will do is we will try to directly go into the circuit design and see what are the things that is available. Okay. So as you can see from the block diagram that We have the power supply connector, we have power management, then we have this particular microcontroller which is going to be S32K with 64 pin. We have connected with like ambient sensors, NTC sensor for temperature sensor. Then we have humidity sensor as well, which can give you the humidity of the environment. We have CAN transceiver, LIN transceiver. Then we have microcontroller ADC utilization to measure some of the voltage levels and all. We have reset circuit for microcontroller. We have given one audio buzzer as well, like magnetic transducer we have given, so that you can use them for some audio purpose or maybe alarm purpose and all. Then we have temperature sensors, we have EEPROM. If you want, I can have like I2C interfacing as well as SPI interfacing. However, internal EEPROM is also there, so internal is also there. In addition to that, two extra EEPROM I have put it here in the circuit. As I told you already, like CAN and LIN transceivers, you can remove that. Then we have dip switches, we have push buttons, we have LEDs for user interfaces. Okay, we have programming connector, SWD wiring is there, so that we will see. Then we have IO expander. So if you are running out of your GPIOs, I have put one IO expander using SPI, and in that case you can increase up to around 16 like GPIO extra. Then we have ADC with SPI, a separate ADC is there with 16-bit ADC I have used using SPI. And then we have UART to USB bridge, and as well as we have one DAC that is going to be 16-bit DAC. Okay, so that can be used for several other purposes. Okay, all right. So let's roll into the circuit. So as you can see, very nicely it is maintained here. The symbol that has been made is very nicely in the form of like a port pin wise. So you can see PTA 0 to PTA 13, similar to that PTB 0 to PTB 13, and PTC 0 to PTC 17. Similar to that we have PTD and PTE. So there are total 5 like ports are there, like port A, B, C, D, E. We have the power pins right side nicely put it here, VDD1, VDD2, and it is analog input, that is VDDA. We have reference as well. If you want, you can give external reference, otherwise directly you can sort this one. And then we have the ground pin. Okay, so we'll talk about the pin mapping separately one by one once we start with our like peripheral circuitry. So let us start with programming. So programming, you can see we have JTAG programming here. So JTAG programming is nicely made in such a manner that it can also support for your SWD programming. Okay, so SWD programming also it can be supporting directly. You don't have to use another extra connector for serial wire programming. Okay. Then anyway, one more extra like 6-pin connector I have used for just for SWDIO programming. So if you want, you can utilize that one, otherwise you can just discard this in your circuit. Okay, instead of using the internal oscillator or like for clock frequency, what I have done is I have used an external 12 megahertz crystal oscillator with current limit and all those things. Sorry, it has to be actually in this point. Okay, so this one should be connected directly this, and you put one resistor here. Okay, I'll be giving you this correction. Okay, we have one reset circuit here which is going to reset the microcontroller by pushing the like push button here. Okay, coming back to right side, we have the like decoupling capacitor and bulk capacitor connected here, as well as we have the like if you want, you can remove this one, this resistor, and put this ferrite bead. So this ferrite bead is actually used to filter out the power supply for analog supply voltage. So analog supply voltage level can be utilized directly at this point. Okay, right side you can see we have the PWM connector. So total 6 PWMs are used. These six PWMs can be used for your motor driving application or something like that. Okay, so I've used like PWM 0, 1 and 2. then we have 3 4 5 6, 3 4 5, okay. 2 is here. All right, so hope you have now a complete understanding of programming and decoupling capacitors and PWM connector, and then we have crystal oscillators, we have reset switch, and this is the particular microcontroller symbol. Okay, now let us get into the second page. So what we have here is we have power supply management. Power supply. So in this power supply, what I have given is we have the external connector which can take up to 66 volt to 18 volt. So you want, you can add a battery directly, or you can give a power supply from your DC-DC power supply. Otherwise, you can connect a adapter jack as well, which generally comes as 6 volt 2 ampere or 12 volt 2 ampere. You can add directly. Okay. So it has been protected with a diode so that it doesn't go into reverse direction. Okay, that is one thing. Another thing is, after this V in A, this is going to go into this particular switching regulator. This switching regulator is going to give you 5 volt 2 ampere output. So 5 volt 2 ampere output you are going to get at this particular point. And this is very nice, like switching regulator from analog devices. This is also going to give you, like one power good, or like let's say once reset. So this reset is actually going to be used to indicate your power supply output. So whenever it is glowing, okay, it means it is it is good. And whenever this LED is not glowing, it means it is having some fault. Okay. So once there is a problem, then this reset will go down, and this is how this will stop glowing. Okay. To convert this 5 volt to 3.3 volt, we have a linear regulator that is there from ROM semiconductor. So in that, I have used 3.3 volt, zero point 0.5 ampere, that is 500 milliamperes, and that can be used. If you want to power up your microcontroller through a USB or something like that, what you can do is you can just sort these two like jumper, so that instead of taking 5 volt from VCC, it will be taking 5 volt from V bus. Okay. So if you do not want to use V bus like a your USB, then you have to sort these two. And if you don't want to sort anything, you can remove this and just connect this particular resistor. So this is enough. Okay. So in your complete circuit, actually this will be available. You don't have to use separate jumper for this. Okay. So hope you guys are clear with the like a microcontroller power supply management, and here even 3.3 volt indication is given by one of the LED using this particular LED. Now interchangeably this VCC, that is VCC as well as 5 volt, both are being used interchangeably. Okay, so that's not a problem. And another point is 3.3 volt will also be named as VDD. So 5 volt will be used as VCC as well, and 3 V3 will be used as VDD. So that is to be understood. Okay. Coming back to the next part, so let us start with one by one. So we have a like a audio buzzer that is being driven by one PWM signal. Okay, so 2.71 kilohertz you have to give to like give that beep sound. Okay. We have EEPROM using I2C interface. So this EEPROM, 4 kilobits of EEPROM is used from microchip technology. So that is using the I2C like application. We have one more 256 kilobits of EEPROM that is also there from microchip technology, and it is using your SPI interface. Okay, so if you want, you can like test your capabilities using the I2C EEPROM as well as SPI interface EEPROM. Then we have here, as you can see, we have a potentiometer with 10 kilo ohm, like resistance, and this can be going to your potentiometer ADC. So you want, you can, like test your ADC's functionality, as I have been telling you for, like couple of videos, last couple of videos. You can see that as well. Now coming back to the testing of your power supply level, so 5 volt is like tested using this particular like a voltage division, and then we have the op amp as filter, op amp as buffer, and after that we have one filter, and then it is going to go ahead with your ADC 5 volt measurement. Okay. Coming back to 3.3 volt, so 3.3 volt, you can see we have again one like a voltage division. If you want, you can do a voltage division as per your requirement. That's not a problem. Just try to make sure that your voltage level doesn't reach more than like 2.5 volt or something like that. Okay, so that's the understanding you should have. That's how you have to like make a voltage division here. And this particular microcontroller has been used as a buffer, and then we filter, then it is going to go ahead with your ADC. Coming back to one of the like temperature sensor, analog temperature sensor, so very nicely it has been used and it is going to go to your temp sense 1 ADC. So there are 4 ADCs that you can see. One is here, one more is for voltage measurement, one more is for 5 volt voltage measurement, then we have temperature sensor measurement. Okay. All right, so now let us start with the next one. So next one, you can see we have user IOs. Okay, user IOs. So in user IOs we have push buttons. So push buttons, it has been made very nicely using like filters and removing the debouncing effects by using the capacitances and all those things. So that's the pretty good thing that we have done here. And PB0, PB1 will be actually used to connect to the microcontroller pins. So those will be acting as a input pin. Similar to that, we come to the dip switches. So dip switches, actually it is used to configure your lines like high or low. So left side it is open and right side it is closed. So once it is in closed position, the dip switch level will be considered as high, and once it is in open position, the dip switch level will be considered as low because they have been pulled down to ground. Now let us talk about the LEDs. So as you can see, two LEDs has been used where my microcontroller pin will be acting as a output pin. Then these two LED has been used where my microcontroller will be acting as a sink. Okay, so here it is acting as a source and here it is acting as a sink. If you have to drive the LED with very high current or something like that, you can directly drive through the like main power supply of 3.3 volt or 5 volt, whatever you want, and then you will be actually monitoring this particular MOSFET using your IOs. Okay, so microcontroller IOs will be just helping you to switch on, switch off this particular MOSFETs, and this is how you will be able to understand. We have put here two like a touchpad as well. So these two touchpad can be designed on your PCB with proper meshing and everything, and they have been used in a like a differential fashion. You want, you can utilize it like that. Okay, so we have touch ADCB, touch ADCB like ADC1B and 2B, similar to that ADC1A and 2A. All right, so hope you have a very good understanding up to this. What we will do now is we'll keep it up to this and next part of the circuit we'll explain you in the next session. Thank you.